In this video, we will talk about MVC, which stands for Model View Controller. We will first take a deep dive to understand what MVC really is. Then, if we really want to get a good grip of the concept, we will look at one example in which we will put MVC in practice by creating an overview design for an app, and we will close by looking at some of the benefits of using MVC in our day-to-day software development. So let's get started. MVC is one of the programming design patterns used in the industry today. A design pattern, in general, is a way of structuring or organizing the code in a software application into separate groups, or camps. Each of these groups gets its own role and responsibility in the overall project. In addition, a design pattern also defines a set of rules on how these different camps should communicate with each other. It all comes down to separation of concern, something very familiar to those used with object-oriented programming. It is important to note that MVC is not just used in Swift, but with many other programming languages and technologies. This channel is focused on learning Swift, though, so we will talk about MVC in the context of the Swift programming language. Let's dive deeper and take a look at how these camps or groups and the communication between them are defined by the MVC design pattern. As the name implies, the MVC design pattern divides the code into three separate elements: the model, the view, and the controller. First, we have the model, which represents the data in the app or the software business logic, the rules of the application. This is the what of the app, what the app is really about. But it contains no information regarding how the app is displayed on the screen, and it is completely user interface independent. This is a key separation of concern. Second, we have the view, which represents the user interface. It is what the user sees on the screen and is directly interacting with. The word view is singular, which might be confusing at first, because the view represents all the elements that make up the user interface: buttons, tables, images, pickers, and many more. The truth is, there is always a single root view, and all other user interface elements are subviews of this root view. The view is the how of the app, how the app looks and feels on the screen. But all of these user interface elements on the screen are built in generic form, completely untied to the functionality of any particular app. A button, for example, is designed to be just a button, without knowing what the button's effect will be in an app. All that the button knows is to show itself in a particular position with a font and a color and other such properties, and who to notify when the user taps on it. That's it. That is the entire responsibility of a button. Of course, in order for the app to work and do something, there needs to be some other party whose role is to listen to these notifications and execute some kind of functionality. Is that going to be the model? Absolutely not. The model needs to remain completely independent from any user interface event. In charge with listening what the view has to say is the controller, the third and last component of our MVC. This controller sits between the model and the view and acts like a mediator between them both. It controls the other two elements, hence the name controller, being responsible for handling all the communication between both of them. Basically, the controller's job is to interpret raw data coming from the model, format that data, and present it to the user by telling the view to display that formatted representation. In addition, the controller needs to react to user gestures and interpret those gestures as data input in order to update data in the model. The controller usually owns both the model and the view and knows everything about them both. It has to know all that they can do in order to do its job as a controller. The controller sends commands to update data when it needs to communicate with the model, or it can make requests for data. The controller can do that because it knows what commands the model accepts. It knows everything about the model. Similarly, when the controller needs to update what the user sees on the screen, it sends update commands to the view. It owns the view and knows everything about the view, so we can do that. Because of this ownership, the reference from the controller to both the model and the view are called strong references. When an object owns another object, it holds a strong reference to the object that is owned. A strong reference ensures that as long as the controller is still active in memory, the model and the view will not be released from memory. Now, this type of ownership is not the same in the other direction. The model, for example, does not own the controller and knows nothing about the controller. When the model needs to communicate changes in the data, it sends blind broadcast notifications. These are blind because the model does not need to know which object exactly will receive them and what that object, or sometimes multiple objects, can do. Any object that subscribes to those exact type of notifications will receive them. Of course, the controller knows everything about the model and therefore can subscribe to the proper notifications. This type of reference is called a weak reference. The same is true when it comes to communication from the view to the controller. The view does not own the controller and in fact knows nothing about it, but it needs to communicate user interface events, such as a tap on a button, a scroll of a list, a pinch to zoom, and so on. This type of communication is done by target actions, which is just another type of blind broadcast notifications. The controller, which knows everything about the view, sets itself as a target for these actions, specifying which action or piece of code to execute when the user event takes place. But the view will send these notifications without knowing anything about the object receiving them. Therefore, again, we have a weak reference back to the controller. Some views can also use this type of communication to ask for more details. This is called delegation. For example, when the user scrolls a list, the view will ask the controller what to display next. Please note that while the controller can communicate back and forth with both the model and the view, there's never ever a direct communication between the model and the view. It is the job of the controller to mediate between the data and the user interface. The model needs to remain completely UI independent. In most cases, it is a database backend combined with some business logic, such as filters when data is requested or validation when new data is created. The model has no business talking directly with the user interface, with the view. On the other hand, the view is composed of subviews such as buttons, lists, bars, labels, speakers, switches, and many, many more. These are all generic objects that should never hold data directly. These only display for the user some representation of the data, formatted properly by the controller, while the source of truth for the data always remains in the model. Alright, if we really want to get a better grip of this entire MVC idea, it will help to take some time and look at a good example of MVC in practice. For our example today, we will design the MVC components for a game called Match Match, also known as Match Up, Memory, Concentration, Pairs, and many other names. It is a card game in which cards are arranged randomly on a surface and placed face down. The player starts by turning over 2 cards and tries to memorize them. If they are a match, the cards are removed. If not, the player turns over another card, while the first 2 cards are turned face down. The player continues to turn over cards, trying to match a card already turned face up. At any moment in time, there can be only up to 2 cards turned face up. When a pair is matched, the pair is removed. The game is over when all the cards are matched up, and the score of the game is the number of flips taken to end the game. The smaller the score, the better. Let's start by designing the model first. The model will incorporate both the data and the logic of the app. Let's call it simply game. The first thing we need to come up with is an initializer, and we need to decide on what this game will require from the start in order to exist as a game. I came up with this init collection, where the collection can be a generic collection, meaning a collection of anything at all. It will not matter to the game the type of the elements in this collection, as long as all the elements are of the same type. Working with generic types can be very powerful. Please note this question mark written after the init. What is up with that? This is called a failable initializer, meaning it can fail if the argument doesn't follow some particular constraints that we can decide on. It can be indeed a collection of anything, but it should not be empty. A game initialized with an empty collection, or collection of nothing, will not make sense to exist, in which case this init will return nil, meaning it will not exist, it will not initialize. But we still have lots of freedom when it comes to what exactly we can put in this collection. A collection of emojis will be a great example of a collection that we could feed to the initializer. Or we could choose to have a collection of integer numbers if we want to. Or even better, we could have a collection of illustrations. It does not really matter for the model as long as all the elements are of the same type. Once the model has an initial collection, it will start consuming the collection and create a pair of cards from each element in the collection, a pair of cards stored somehow in the model itself. After the cards are all created, it will shuffle them all, getting the elements in a random order. And it will probably mark them all as turned face down. But nothing is yet visible to the user. This is just how data will be represented in memory. Besides the initializer, we will need a way to actually play the game. A function called choseCardAtIndex will do just that. The controller, who owns the game, will call this function every time the user flips a card over. When the function is called, the game will do the play and will return a new state of the game back to the controller. This game state will have to be a custom data structure the model has defined, which the controller can understand and use to display a visual representation of the current state of the game on the screen. Now that we have the model, what will the controller have in its arsenal? Well, it will definitely need some card buttons. This will be in an array of generic user interface buttons, and the controller will be in charge with instructing the view about arranging them in a layout on the screen. The next thing needed will be a label to show the current number of flips. When the game is over, we will need a button to start a new game. And it wouldn't be a bad idea to have a label that would show an error message when, for example, the user taps a wrong button. And finally, the controller will own a game, the same game object we have previously created in the model. Then, the controller will have to have the means to react to user gestures. For that, we will use target actions, which means the controller will set itself as a target for particular gestures. The first one will be a function called userTappedOnCard button, which will be called for any of the buttons being tapped, hence the sender argument. This is where the controller will need to understand which button is the sender and send as a response a choseCardAtIndex command to the model with a proper index. Then, of course, we will need another function to respond when the user wants to start a new game. So let's imagine we are playing the game in slow motion. The user taps this button in the second row, first column, which results in the view sending this message, userTappedOnCard button, to the controller. The controller concludes the button is at index 3, since indices in Swift start at 0, not at 1, and sends this message, choseCardAtIndex3, to the model. The model does its thing and returns a new game state to the controller. The controller then instructs the view to mirror the data received in the new game state from the model, which means the button at index 3 will be shown face up, and the bottom label showing the number of flips will be updated. If the user taps on the same button again, the view will, of course, send the same message to the controller as before, userTappedOnCard button. It is not the job of the view to understand this is not a valid tap at this point. The view is not concerned with the rules of the game. In fact, the view does not need to know what happens with the messages about user gestures. And it is not the job of the controller either, which means the controller will send the same message, choseCardAtIndex3, to the model just like before. Now the model will be the one detecting this last tap is invalid by applying the rules of the game, and it will return a new game state to the controller, a state that will now contain an error data object. The controller will interpret the new game state received from the model, and will tell the view to leave each of the card buttons the same, but this time display an error message. If the user taps another button now, the one on the third row last column, the view informs the controller of the tap gesture as usual. The controller determines this new tapped button is at index 8 this time and sends the message to choose card at index 8 to the model. The model takes that information and returns a new game state back to the controller. The view is now told to reflect visually the new game state on the screen, which means two matching cards will now be displayed face up in a recently matched state, let's say represented by an orange background. The error message will disappear since this new state does not contain an error, and the number of flips displayed on the bottom will be updated. If the user taps now the button on the second row, second column, then same as before, the view will notify the controller of a button being just tapped. The controller will determine this button is at index 4 and will send a choose card at index 4 message to the model. The model will play the game with the new information and return a new game state back to the controller. The controller will instruct the view to reflect this new game state on the screen, which will mean the two previously matched cards will disappear completely, a new card will be displayed face up, and the flip count display on the bottom of the screen will be updated. And this cycle continues until the game is over. Now, let's look at some of the benefits of using MVC design pattern in building a software project. It all boils down to separation of concern. Each of the camps, the model, the view, and the controller, are basically designed to be completely distinct entities, having their own clear and separate purpose. And yes, there needs to be communication between these camps, but the communication also follows clear rules, which eliminates unnecessary communication, such as between the model and the view directly. This design can lead to faster development process. First of all, because multiple developers can work on the same project at the same time, since working on separate modules will not impede on each other's work. But even when the entire project is developed by a single developer, being able to focus on a smaller problem at a time usually saves a lot of time. The pattern can also lead to projects that are much easier to update and debug. Imagine how much more complicated it will be if a flat tire on a car will require some kind of work on the engine in order to fix the tire. Same here. A software bug can be detected much easier and fixed if it is part of a much smaller, decoupled part of the entire software. Another benefit of MVC design is low coupling. Low coupling ensures ease in making changes and adapting the software project to new requirements. First of all, low coupling gives the ability to provide multiple views for the same data model. That's right. Once the data model is designed to be completely independent from the user interface, we could easily apply it to different views. For example, our match-match game designed with an iPhone in mind with only 12 cards can be easily translated to run on an iPad having 54 cards without making any kind of code changes in the model. Now that's pretty cool. At the same time, low coupling also makes it easy to swap the model altogether without having to change the code in the controller or the view. We might decide to change the rules of the game, for example, and an update like that will require code changes in the model only. The user will still have to tap a button and get a new state of the game every time in return. Lots of time savings when doing low coupling programming. Well, this was pretty much what I wanted to say about this concept called MVC. I hope this video did provide some value for you. If so, please subscribe and turn on notifications so that you will not miss any of the future videos. This is my very first video, so please feel free to give me feedback in the comments below and let me know what you think. Thank you so much for watching this video till the end, and I hope to see you in the next one.